The same ideas from the previous section can be applied to polynomials of degree 3 this time. So p of x equals ax cubed plus bx squared plus cx plus d, and a does not equal 0. Well, by the fundamental theorem of algebra, we can write it as a times x minus r1 times x minus r2 times x minus r3, where the ri's are complex numbers. Then by Vieta's formulae, we know that negative b divided by a is r1 plus r2 plus r3, and we can write this as the sum of I of ri. C divided by a is equal to r1 times r2 plus r1 times r3 plus r2 times r3, which is the sum of all I does not equal j, ri, rj, where I and j are from 1 to 3. And then finally, negative d divided by a is r1 times r2 times r3. And if you want to write it in an even more convenient way, that's easy to remember, you can just think of it like this. Negative b over a, sum of alpha, so the sum of each of the roots. Positive c divided by a, sum of alpha beta. And then negative d divided by a, sum of alpha beta gamma. And if we were doing a polynomial of degree 4 or higher, the next one would be positive e divided by a equals sum of alpha beta gamma delta. So in this case there would be 5 roots, and we'll be taking the sum of all of them, except for one being multiplied together, and then just do it across all combinations of that. But we'll come back to that later. So the coefficient of the highest power of x cubed is just a, and then we know that b over a negative, sum of the roots individually, c divided by a positive, sum of all pairs of the roots, each one only one time. So r1, r2, r1, r3, r2, r3, so only one time for each pair. So 3 choose 2 equals 3 combinations. And then negative d over a, all of them multiplied together. And in this case, since there's only 3 roots, there's only one combination where all of them can be multiplied together. So sum of single roots, sum of double, and sum of triple, negative, positive, negative. So should be nice and easy to remember. Okay, let's look at some examples. First one, exercise 1.5. Find a cubic equation with roots 2 plus or minus I and 3 by making use of the relations between the roots of a cubic equation and its coefficients. So there are infinitely many of these things, which means we can let our choice of A be any number we like. So I'm just going to choose it as 1 for simplicity. So we got z cubed plus bz squared plus cz plus d equals 0, and then making use of our formula before, we know that negative b divided by a, which is just 1 here, is the sum of the single roots. C divided by a is the sum of all pairs of the roots, each one once, and then negative d divided by a is the sum of all of the roots multiplied together, in this case, alpha, beta, gamma, so it's just all 3 of them. Okay, so we can quickly find negative b, it's just all of the roots added together, 2 plus I plus 2 minus I plus 3, and then we just get 7. So that tells us that b is equal to negative 7. Alright, for c, we need to multiply them, or multiply all pairs of them together. So 2 plus I, c equals 2 plus I times 2 minus I plus 2 plus I times 3 plus 2 minus I times 3. And then we get 4 minus negative 1, so 5 plus 6 or 6, because the plus 3i and the minus 3i will cancel, and then so we get 17. And then lastly we have that negative d is equal to all three of them multiplied together, 2 plus I times 2 minus I times 3, and that is equal to, what do we say, 2 plus I times 2 minus I was? That was 5. So that would be 15, and so that tells us that d is equal to negative 15. And therefore, just going ahead and subbing those values in, we get that our polynomial equation with those roots is z cubed minus 7z squared, and then c was 17, so plus 17z, and then minus 15 equals 0. So that's our answer there. Exercise 1.6 may require a little bit of playing around. The cubic z cubed minus 3z squared minus 6z plus 2 equals 0 has roots alpha, beta, and gamma. So we immediately can see that the sum, since a equals 1 here, we can immediately see that the sum of the singular roots is, well, negative of the sum of the singular roots is equal to negative 3. So that would mean the sum of the singular roots is positive 3. The sum of all pairs of the roots is equal to just the coefficient of z, so that would be negative 6, and the sum of all triples of the roots, which in this case is just alpha, beta, gamma, because there's only 3 of them, is equal to negative 2. Okay, find a cubic equation with integer coefficients that has the roots alpha, beta divided by gamma, beta, gamma divided by alpha, and gamma, alpha divided by beta. So, one thing that we're going to need to know is the sum of them. Alpha, beta divided by gamma, plus beta, gamma divided by alpha, plus gamma, alpha divided by beta. And so if we simplify this into one fraction, we can see that, well, it's going to be alpha squared, beta squared, plus beta squared, gamma squared, plus gamma squared, alpha squared, divided by the 3 of them multiplied together, alpha, beta, gamma. Now we know the one on the bottom, alpha, beta, gamma, it's just negative 2, but the one on the top is a bit of a problem. However, we can find it using a bit of trickery. Maybe you stare at it for a little while, and then you make the connection that, okay, we actually know alpha, beta plus beta, gamma plus gamma, alpha. That's this thing here. It's negative 6. So that's alpha, beta plus alpha, gamma plus beta, gamma. Alright, and this alpha squared, beta squared is the same as alpha, beta squared. So we can go ahead and use our little trick from before. If we square this, alpha, beta plus beta, gamma plus alpha, gamma squared, that's going to equal what we have on the top, alpha squared, beta squared, plus beta squared, gamma squared, plus gamma squared, alpha squared, plus 2 times all the other products. But all the other products are going to look like this, alpha, beta times beta, gamma, so that would be alpha times beta squared, gamma, and then, well, alpha, beta times alpha, gamma, so that would be alpha squared, beta, gamma. And then the last one will be these 2 multiplied together, so beta, gamma plus alpha, gamma, beta, gamma times alpha, gamma, so that would be alpha, beta, gamma squared. Okay, so just to arrange this in a nicer form, it's still equal to alpha squared, beta squared, plus beta squared, gamma squared, plus gamma squared, alpha squared. But there's a nice little factorization we can do here to get everything in terms of things that we already know the answer to. And the factorization is that we can pull out all 3 of them, alpha, beta, and gamma. So 2 times alpha, beta, gamma, and then, well, inside the bracket, what's left, times that by alpha to get the middle one, times by beta to get the first one, and times by gamma to get the last one. And so all of a sudden it's in terms of things that we already know. So substituting everything in, we've got alpha beta plus beta gamma plus alpha gamma is equal to -6. So we got -6 squared is equal to the thing we're looking for, alpha squared beta squared plus beta squared gamma squared plus gamma squared alpha squared plus 2 times alpha beta gamma, which is -2, times alpha plus beta plus gamma, which is the sum of all three roots, which is 3. And therefore we see that alpha squared beta squared plus beta squared gamma squared plus gamma squared alpha squared is equal to 36 plus 12. So that will be 48. And then on the bottom there, alpha beta gamma is -2. So it should be -24. Okay, so we just calculated that alpha beta over gamma plus beta gamma over alpha plus gamma alpha over beta is equal to -24. So that's going to be the negative of the coefficient in front of our z squared for our polynomial. Alright, next we're going to find the product of any two of these roots multiplied together and then add that together. So the first two is going to be alpha beta squared gamma divided by alpha gamma plus, and then the first one times the last one would be alpha squared beta gamma divided by beta gamma, and then plus the last one would be alpha beta gamma squared divided by alpha beta. Alright, and we can clearly see that there's a lot of cancellations. So we're just left with alpha squared plus beta squared plus gamma squared. And we can find that fairly easy. It's just equal to alpha plus beta plus gamma squared minus 2 times the sum, well, the sum of the pairs of different roots. If you don't believe me, check by doing the multiplication yourself by hand. Okay, and then, well, we already know these values. Sum of alpha plus beta plus gamma is just equal to 3, so 3 squared minus 2 times the sum of alpha beta, which we figured out is -6. So that would be equal to 9 plus 12, so that would be 21. And lastly, to find the negative of our to find the negative of our constant coefficient, we just need to multiply all three of the roots together, and that's nice and easy. It's just going to be well, alpha squared beta squared gamma squared divided by, and then on the bottom, alpha beta gamma. So of course that's just equal to alpha beta gamma, which is equal to -2. And so we are finally ready to answer the question. This was the sum of the roots. We're going to choose our a value to be 1 because we can find any cubic equation. So we can just start out with z cubed. Okay, since the sum of our roots is equal to -24, that means the coefficient of our z squared is going to be +24. So +24 z squared. And then we found that the sum of all pairs of products of the roots is equal to 21. So that is also going to be the coefficient of our z. And then finally, all three of the roots multiplied together is -2, which is going to be the negative of our constant coefficient. So our constant coefficient is going to be 2 again. And then that's, of course, equal to 0. So that should have these roots here by Vieta's formulae. And a nice handy little formula to remember. It came up in the middle of that last question. It's basically saying if you have a plus b plus c, you square it. It's the same as the sum of the squares plus 2 times the sum of the products of any two of them. So in our notation, we would write it like this. Sum of alpha squared is equal to the sum of alpha squared plus 2 times the sum of alpha beta, where we have roots of a cubic equation that are alpha, beta, and gamma. On the other hand, if we want to extend this to the case where we have roots of a quartic equation, so that's a polynomial of degree 4 equal to 0, so alpha, beta, gamma, and delta. So if we're going to write it in this form, it would be the sum of alpha squared is equal to the sum of alpha squared plus, and then again it would just be 2 times the sum of alpha beta, except in this situation here we would have 4 choose 2 equals 6 combinations instead of 3 choose 2 equals 3 combinations like we did in the case where there were 3 things added together and then squared. So yeah, if you're gonna use summation notation and be completely proper about it, I guess you would have this, but I would just suggest getting used to doing it this way, because you're going to do so many of these things and it's just going to be much faster to write sum of alpha squared, sum of alpha beta, or that kind of thing. So yeah.